So, in the last lecture we have been discussing about the different internal architectures of standard families like Fermi family of GPUs. So, in this lecture this is going to be the last part of our topics on GPU architecture basics. We'll just introduce you to this idea that whatever we have been discussing, maybe they are more about GPU architectures, but we also need to discuss a bit on the current reach of GPU architectures. Otherwise, one may just start thinking that okay, a GPU is nothing but a card that you attach to a desktop system, or maybe it's also a specific kind of processing hardware which is present in the cloud in these high performance systems around us, which are executing all the nice and fine workloads that kind of drive our day-to-day lives and all that. However, in contrast, there is a significant amount of GPU computing going on in devices around us, which is something many of us may not be very much aware of. So, this is basically in the domain of embedded GPUs. So, just to make my point again, it's not that we have GPUs present in our workstation class systems, our laptops for gaming workloads, or in the cloud. They are also present around us in mobile systems, in the embedded space, and also in autonomous driving systems which are being slowly getting built. So, coming to this domain of mobiles. So, in most modern smartphones, you have a GPU core which is responsible for accelerating the graphics or the rendering pipelines for your mobile screen. A very popular choice of GPU core which is provided by ARM is the Mali GPU core. It is present in several families of processors. For example, the Samsung Exynos chips which are present in many of the Samsung smartphones. There is also another very popular offering called the Adreno GPUs, which are present in almost all Qualcomm chips. There's the Snapdragon chips which also actually drive mobile smartphones, a significant number of mobile systems. So, more or less these are the two popular choices of GPUs. Of course, there are many other choices also, but these are the significant ones. So, they can be used to accelerate the graphics workloads, improve and provide a smooth rendering in the smartphone display. Also, they can be leveraged for doing compute tasks, just as they can be leveraged for doing compute tasks in the desktop or the HPC systems. So, apart from mobile GPUs, we have significant amount of offerings from NVIDIA in the embedded space. For example, this Jetson family of devices like Jetson T, Jetson Nano, which is the smaller IoT type of system offering, and also the high-end AGX Xavier kind of system. So, essentially these are all embedded boards comprising multiple cores. So, they have a processing system, they have an SoC which has got multi-core ARM CPU plus a GPU comprising cores in varying numbers, maybe starting from 128 to up to 512 cores inside the GPU. So, and that depends on the kind of embedded board we are talking about. If we talk about Jetson Nano, this is the most lightweight embedded boards which are available from NVIDIA for accelerating tasks like deep learning or AI in edge devices, not in cloud systems, but in edge devices. And the next important class of systems where we have significant drive coming from GPUs is the NVIDIA drive systems. So, these are the system architectures which are used for implementing autonomous cars, which are used for implementing the ADAS functionalities and autonomous driving systems in cars. As we are, I think everybody here is aware of the company by Elon Musk who manufactures the Tesla cars, and it happens to be the case at least that many of these companies actually implement their autonomous driving computers inside the cars on NVIDIA's drive kind of platforms. They also implement significant number of ADAS functionality. So, what is ADAS? It's autonomous drive assist systems. So, it's just to introduce you a bit to this topic. I mean, we always keep on hearing about autonomous driving systems which are present inside cars, so that a car is going to be driven automatically in a like a driverless fashion, where there would be a deep learning computer sitting inside it. Which is that computer? Is this NVIDIA Drive kind of system? It's not a normal computer, but it contains a significant amount of engineered SoCs containing specific GPUs specialized for this purpose, and also ARM cores and other kind of cores. So they will execute a deep learning pipeline which will try to take all the driving decisions on the behalf of the driver, when to accelerate, when to turn right, when to turn left, when to change the gear and all that. However, while these are still, some of them are in experimental stage, but there are significant vehicle functionalities which get automated. It's not that the vehicle has always got to move in an autonomous mode, but these are known as drive assist systems. That means the vehicle is not fully autonomous, but certain operations of the vehicle can be automated. For example, a park assist system, which can park the vehicle slowly automatically without assistance from the driver. So all those kind of systems, the assist systems, they form this kind of ADAS functionalities for a vehicle, and some of these ADAS functionalities also are implemented using AI-based techniques, and for such AI-based techniques, these NVIDIA Drive systems are popularly used. So coming into this idea of mobile workloads, like what is the GPU doing inside a mobile? As we discussed, that the primary reason can be for driving the huge amount of graphics computation required for rendering nice videos or high speed gaming graphics in a smartphone's big display. Also, it can be used for compute loads. For example, trying to do some AI based inferencing on a mobile platform. If you have to do an inferencing task on a mobile platform, for example, these smart cameras and live recognition systems, you are taking a picture in using a mobile camera and trying to also recognize the people in the picture. That is also an AI task, which if it can be executed on the mobile, can save a lot of communication with the cloud. So for this also, the mobile GPUs can be leveraged. Now in this slide, we present a typical picture of how current generation mobile SoCs are organized. This is just a representative picture, and it's trying to show that a mobile SoC can be quite heterogeneous in nature. For example, it can have multiple CPU systems along with GPU cores. So here in this picture, we show a interconnect system which is connecting a cluster of CPU big cores. So these are typical kind of cores which are provided by ARM, and there can be a cluster of CPU small cores, and then you can have a Mali based GPU. So why are these CPU big cores clustered together? Because they can, by big core I mean it is clocked at a higher rate. It can have more number of SIMD units present. By small core I mean it's a low power core having low amount of processing bandwidth. They have their internal L2 caches. So that again the structure, as you can see, is similar to our SM designs at a larger scale for Fermi. So the L2 is unified. It is available to all the different CPU big cores. Inside them we will have the L1 cores. Again the L2 is again unified and is available individually for all the CPU cores. These big cores form a cluster, the small cores form a cluster, and again here you have the Mali GPU with 4 GPU cores. Again they are connected by unified L2 cache, and there is a memory management unit. So why is a mobile chip going to be arranged in this kind of way? Well, there are good reasons. As we discussed, that this by big core, it means it can do lot of compute, but also executing and consuming more power. These can do less amount of compute because they are clocked at a smaller frequency, but they will also take less power. And for doing graphics workload processing, you can use the Mali GPU. With this fabric of heterogeneous cores available on the mobile platform, it provides a significant handle to the developer to decide and map workloads across this whole CPU GPU system. So, if I have a heavy workload, I will like to map it on this big cluster. If I have a lightweight workload, or maybe I have a workload which is a mixture of heavyweight tasks and lightweight tasks, I can decide and accordingly intelligently map as a programmer the tasks into the big cluster or the small cluster. If I have a graphics workload, I can intelligently map it to the Mali GPU. So, all these options are available in a modern mobile SoC, which is kind of heterogeneous in nature. Now, of course, what are the different programming languages available from the SIMD paradigm? Now, we are in this course we are always speaking about SIMD or parallel programming languages, which are of the style that is single instruction multiple data. So, from that perspective, we have parallel programming support available for mobile devices in terms of languages like OpenCL. So, they provide a data parallel. It's a language for writing code which is data parallel in nature, and the code will execute in a mobile device. Also, if you are looking into the well-known Android SDK, Android SDK provides a facility called render script, through which you can specify a data parallel program that can be executed inside this course. Now, coming out from the mobile space, let's also take a look into desktop systems. Now, in desktop systems, of course, you can add an NVIDIA card and you have a GPU, but it's not necessary that without that card you don't have a GPU. Now, this is something new, right? Because we have always thought that a GPU comes as a separate card. Well, in modern CPUs, starting from if I go into AMD's offerings, starting from AMD's Fusion, and also if I look into Intel's offering, Intel's Ivy Bridge architecture, so they provide a kind of CPU which also has a fused GPU inside it. So, it's like an integrated CPU-GPU system. So, the difference between a large GPU card and this kind of system is that you have a small graphics processing part sitting on the same die, and they are sharing the same physical memory, so that zero copy transfers can be employed. So, essentially, if you have a CPU chip and you attach a separate GPU card on your desktop system, then they communicate through the PCI Express, and there is always this communication overhead. So, until and unless you are going to throw some significant amount of parallel computation for the GPU, maybe the mapping doesn't make sense, because apart from gaining in terms of parallel processing, you are also losing in terms of the data transfer overhead. But that problem is not present here, because CPUs and GPUs access the same physical memory. So, that there is no physical data transfer, or you can have this logical zero copy transfers that can be employed. So, these zero copy transfers ensure coherency, and essentially what they do is they translate the pointers to memory buffers for a common address space shared by both the CPU and GPU, but physically there is no transfer of data because everything is in the same memory space. But again, there is a bad effect due to this. So, since the memory space, the physical memory space is shared between the CPU segment and the GPU, both of them compete for the memory bandwidth of the same shared memory, and that can create interference issues. So, I mean, if both of them are trying to compute for the same segment of memory, one of them will always face a stall, and due to that the overall computation will get slow and all that. So, there is always a good thing and also a bad thing with respect to this kind of an arrangement. Now, something more we have is with respect to this integrated GPUs. So, in recent times, from Intel Broadwell architecture and beyond, CPUs and GPUs were further integrated. So, earlier there was this CPU chip and CPU and GPU together sitting on a same chip, and they were actually looking into the same physical main memory. So, but from this Broadwell time, what happened is they added a third level of cache, which is the shared last level cache or LLC. So, earlier it was not there. So, earlier you had the GPU with GPU cache, CPU you have multiple cores of the CPU, each of the cores will have their L1s for instruction and data, the L2s, and that's all, right. So, you have these multiple cores of GPUs and CPUs, and they would be accessing the main memory. But from the Broadwell architecture, what happened is that people added this last level cache inside the system. Now, what's the good thing about a last level cache? It provides you additional on-chip memory. So, this helps the CPU and GPU in executing compute kernels on the same data in parallel collaboratively. So, earlier it was not possible, but since I have this last level cache on chip, I can execute on the kernels, compute kernels, both CPU and GPU, and I will be accessing the same data, and coherence of the data will be maintained through that last level cache. Now, coming to this issue of coherence. So, what's the cache really going to do? It's going to take care by hardware of the coherence decisions. But again, this also will introduce some problems with respect to this, which we will discuss. But just to understand the point that to which these systems have evolved, earlier there was only CPUs and GPUs which were integrated on the chip, but with the addition of more cache in the hierarchy, since the cache is also uniformly available to the both the CPUs and GPUs, they don't need to synchronize using the main memory. They can synchronize their computations using the shared last level cache itself. That's the takeaway from this. Now, coming to this issue of coherence and all that, let's jump back to one of our earlier slides to understand it better. So, if you remember, we were discussing, let's take this picture, that you have in a standard Fermi. So, I'm going back to our original discussion on Fermi GPUs, where we have discussed that the L2 is unified and the L1s are distributed across the SMs. Now, observe one thing, since L1s are distributed across SMs, that means each thread can load a copy of data into, the threads are sitting in different SMs, so they can load copies of data and update those data values, and those updates will be visible to L1s. So, it can always happen that across SMs, the L1s have different updated copies of variables. So, that since the L1s are not unified here, I can technically have the L1s which are not synchronized. They are containing different possible updated values of variables, and that may lead to consistency issues with respect to data values. This is something we are not going into detail. We are just trying to give you an idea that what can be a bad thing that may happen due to the memory being segmented here, right? Now, this is something that a programmer also needs to keep in mind and accordingly write the code when he is trying to do a specific kind of computation such that threads across SMs are trying to work on similar data segments. We are just trying to highlight that there can be problems with respect to this which a programmer has to manage. These are the things which we will explore in more detail later on. So, coming back to our current discussion. So, as we are discussing here that since we have the shared last level cache, the good thing is the CPUs and GPUs need not collaborate on data updates by synchronizing through the main memory, but they can do that using this unified cache itself. So, coming to the other kinds of offerings from NVIDIA, that is the Jetson series. So, if you remember, we were discussing that in the embedded space, NVIDIA has offerings from Jetson for different kinds of offerings, the lightweight nano systems, also the heavyweight AGX Xavier kind of systems. So, what are these? So, we take a specific example of a TK1 SoC from the Jetson series. It incorporates a quad-core ARM machine. So, it incorporates a quad-core ARM machine. So, you have 4 CPU cores, each clocked at 2.32 gigahertz, and they are 32-bit systems, and it also has an integrated Kepler family of GPU. The CPUs again share a 2 MB L2 cache, so the L2 is again unified for the CPUs, and the GPU has a 1922 core system and a 128 kilobyte L2 cache. So, the L2 is also unified for the cores of the GPU. Now, what's not shown in this picture is that apart from having these 4 CPU big cores, the CPU part also has little ARM cores. Of course, they are there for low power compute, which is not requiring too much of performance, but then I can always optimize on the power, and then I will map such workloads to the little ARM cores. Again, for increasing the bandwidth of memory access, the DRAM is banked into 32 banks here. Each bank is of size 64 MB. So, this is a typical architecture of a Jetson kind of system from NVIDIA. Now, okay, what are the kind of computers that people are offering for cards? So, this is one such example, which is basically the NVIDIA Drive series of system. So, this NVIDIA Drive PX2 is one of the standard systems that is based on these Tegra SoCs from NVIDIA. So, what is the Tegra SoC? It is another more powerful SoC containing 4 ARM A5 cores and some cores called the Denver cores. That is something that NVIDIA separately created for, for this kind of system, and they also include a GPU from this latest Pascal generation. Now, what is the use of such a high performance system in a card? Like as we discussed, that a card in future will have lot of drive assist as well as self-driving facilities, which are essentially deep learning computers, which also need to deliver lot of vehicular decisions in high throughput inside real time, and those can be implemented in this kind of system targets, and that is one of the reason for building this kind of drive systems, which are much more powerful if we compare them to those in the embedded offering. So, just to summarize, these are the different kind of other systems, other compute architectures which are available to us, which provide several forms of data processing capabilities. You have GPUs available in mobiles, you have GPUs available in the embedded space in form of this Jetson series of computers. You also have heavyweight compute systems involving GPUs built for the NVIDIA Drive systems, which are part of many well-known electric cars, and they provide significant drive assist functionalities there also. So, with this, we will end our coverage of the basics of GPU architectures, and we will shift to the introduction to CUDA programming, and we will introduce CUDA as a language and how to write specific kind of programs for this GPU and leverage these parallel architectures. That is something we will start covering from the next lecture. Thank you.